Scientific explanation has never been a fixed or final structure. It is a living framework that grows, bends, and transforms as human knowledge deepens. To understand how deeply scientific explanation evolves, one must recognize that every era of scientific thought has believed, with confidence, that it possessed the correct understanding of the world, and yet, each era has eventually watched its convictions overturned by new discoveries that exposed hidden layers of reality. The process is not merely a correction of mistakes, it is a reinvention of how humans think, how they observe nature, and how they define truth itself. The evolution of explanation is therefore inseparable from the evolution of human curiosity, because science is a continuous conversation between what is known and what remains unknown, and every discovery forces that conversation into a new direction. In ancient times, explanations of natural phenomena revolved around observable features of the world, patterns in the sky, the flow of water, the change of seasons, the growth of plants, and the motion of animals. People explained these events based on intuition and direct experience. Fire burned because it was hot and alive. The sun moved because it was carried by divine beings. The world behaved as it appeared to behave. These explanations were not naive. They were simply the best organizing principles available in a universe without microscopes, telescopes, mathematics, or instruments. For the people of those eras, these interpretations felt complete and coherent. It was only later, when new tools and methods emerged, that the limitations of such explanations became evident. The scientific revolution marked the first major transformation in the structure of explanation. Thinkers like Copernicus, Galileo, Kepler, and Newton demonstrated that the world does not always obey the patterns of intuition. Objects fall not because they seek the ground, but because gravitational forces act on them. Planets move not in perfect circles, as once believed, but in ellipses governed by precise mathematical relationships. Natural motion follows rules that can be expressed, measured, and predicted. This shift redefined explanation itself. Instead of relying on appearance or myth, explanations began to rely on evidence, experimentation, and mathematical structure. The universe was no longer just a stage for events. It became a system governed by laws. This change, this rewriting of explanation, did not discard the past. It replaced it with a deeper level of understanding grounded in principles that could be tested again and again. But even Newtonian physics, revolutionary as it was, eventually revealed its own limitations. For centuries, it explained the motion of planets, the behavior of falling objects, the flow of fluids, and the mechanics of machines. It became the intellectual foundation of engineering, astronomy, and classical science. Yet new phenomena emerged: light bending near massive objects, the orbit of Mercury deviating slightly from Newton's predictions, the behavior of objects at speeds close to that of light, that could not be explained within the Newtonian model. Einstein's relativity reshaped the very fabric of explanation. Space and time were no longer fixed or absolute. They were dynamic, interwoven, and influenced by mass and energy. Gravity was not a force pulling objects together, but a curvature in spacetime guiding the path of motion. This transformation did not merely add new knowledge, it redefined old knowledge. Suddenly, Newtonian mechanics became a special case within a broader, more flexible framework. Explanation had expanded once again. The same pattern repeated itself in the microscopic realm. For centuries, scientists believed that atoms were indivisible particles. They explained chemical reactions as combinations of these solid, permanent units. Yet experiments revealed that atoms themselves were composed of subatomic particles, electrons, protons, neutrons, and these particles behaved far differently from classical expectations. Quantum mechanics emerged, bringing with it a new style of explanation, one that could not rely on certainty or direct visualization. The quantum world introduced probability, duality, and uncertainty. An electron could behave like a wave and a particle at the same time. A particle's position could not be known with perfect precision. Events could be influenced by observation itself. These ideas challenged not only scientific understanding, but the philosophical foundations of explanation. How could the universe be explained through laws that seemed to defy common sense? How could reality be described when the act of describing it changes what is observed? Yet quantum theory succeeded in explaining what classical science could not. It accounted for spectral lines, atomic transitions, chemical bonds, electrical conductivity, and countless phenomena central to modern technology. In doing so, it redefined explanation once more. Human understanding could no longer rely solely on visual models or classical logic. It required abstract mathematics and a new acceptance of uncertainty. Science had again expanded its boundaries. Every time explanation evolves, it forces us to reconsider what we call fundamental. What seems fundamental during one era becomes superficial in the next. Ancient explanations focused on visible qualities: hot, cold, dry, wet. Classical science focused on forces and motion. Modern physics focuses on space-time geometry, quantum fields, and probability amplitudes. If future discoveries reveal deeper layers of nature, perhaps involving multidimensional structures, quantum gravity, or new forms of energy, our current explanations will appear incomplete and simplistic. This is not a flaw in science. It is the essence of science. Explanation is never final because discovery is never finished. The evolution of scientific explanation is closely tied to the evolution of scientific tools. The telescope expanded the scale of the observable universe. The microscope uncovered the hidden world of cells and microbes. Particle accelerators revealed the subatomic realm. Computers allowed simulations of systems too complex for analytic solutions. Every new instrument opens a door to phenomena previously invisible, and every new phenomenon demands a new explanation. Thus, explanation evolves not only because theories change, but because the very act of observation becomes more powerful. Another crucial driver of evolving explanation is the recognition that different scales of nature operate according to different rules. The laws governing galaxies differ from the laws governing atoms. The behavior of fluids differs from the behavior of crystals. Social systems, climatic systems, and biological systems each require a unique vocabulary of explanation. As science expands into new domains, complexity theory, information theory, systems biology, neuroscience, it becomes clear that explanation must adapt to each context without losing coherence. The challenge is to build a universal understanding that connects these layers without oversimplifying their differences. Furthermore, scientific explanation evolves because human thought evolves. New generations of scientists bring new questions, perspectives, and philosophical assumptions. Cultural and intellectual shifts influence what is considered important, what problems are prioritized, and how theories are interpreted. For example, early scientists focused on structure and stability, reflecting a world view of order and hierarchy. Modern science embraces change, complexity, and indeterminacy, reflecting a world view shaped by technology, globalization, and interconnected systems. The evolution of explanation mirrors the evolution of human thought. One of the most profound aspects of scientific evolution is that knowledge is never isolated. Discoveries in one field reshape explanations in another. Quantum mechanics influenced chemistry. Chemistry influenced biology. Biology influenced medicine. Information theory influenced genetics. Astrophysics influenced particle physics. And now, quantum information theory is influencing both computing and fundamental physics. This interconnectedness means that a breakthrough in one domain can redefine what is fundamental in many others. Explanation becomes increasingly integrated, weaving together multiple layers of reality into a unified vision. Modern scientific explanation is also shaped by technology. Artificial intelligence, complex simulations, and high-speed data analysis allow scientists to explore phenomena that are impossible to examine directly. Explanations built on these tools look very different from explanations of the past. Instead of simple equations or clear diagrams, modern explanations may consist of computational models, probabilistic predictions, or massive datasets. Some phenomena can only be understood through simulation rather than close-form mathematical solutions. This introduces new philosophical questions. Is an explanation valid if it cannot be visualized? Is understanding possible without intuitive clarity? These questions illustrate that explanation itself is undergoing transformation as science becomes more computational. Another feature of evolving explanation is the shift from linear causality to networked causality. In classical mechanics, cause and effect were straightforward. One event produced another in a predictable sequence. But modern science recognizes that systems often involve feedback loops, interdependent variables, and emergent phenomena. The behavior of the whole cannot be understood by analyzing parts in isolation. It arises from interactions. This is true in ecosystems, economies, brain networks, weather systems, and even quantum entanglement. Explanation becomes richer and more complex because it must account for relationships rather than isolated components. At the same time, scientific explanation continues to be grounded in the idea that the universe is understandable, even if that understanding requires new frameworks. The belief that nature has structure, however complex, drives the pursuit of deeper explanation. This pursuit is not only intellectual but technological and human in its consequences. Every shift in explanation empowers new inventions, new therapies, new materials, new forms of communication, and new ways of shaping human life. As explanation evolves, society evolves. Today, science stands at the edge of another transformation. Researchers seek a unified theory that can reconcile quantum mechanics with general relativity, bridging the microscopic and cosmic realms. Others explore dark matter, dark energy, quantum gravity, and the origins of the universe. These frontiers demand explanations that may challenge every assumption humanity currently holds. Just as past discoveries reshaped old explanations, future discoveries will reshape the present. The process is ongoing because reality is far deeper than any single theory can express. Scientific explanation evolves because it is fundamentally humble. It does not claim eternal certainty. It seeks continuous improvement. It welcomes revision. It embraces contradiction as a path to clarity. Every new discovery is not a threat to science, but a gift that expands its scope. Explanation becomes a journey rather than a destination, a growing structure that absorbs new knowledge without collapsing. This strength, This flexibility is what allows science to move forward indefinitely. Ultimately, the evolution of scientific explanation reflects the evolving relationship between humanity and nature. As humans gain more tools, more insight, and more imagination, they are able to see patterns that were once invisible. They move from surface observations to deeper principles, from isolated facts to integrated theories, from simple models to dynamic systems. Every era brings its own understanding of what is fundamental, and every era eventually outgrows that understanding. This continuous expansion is not only what defines science, it is what makes science one of humanity's greatest achievements. Scientific explanation does not simply answer questions. It transforms the questions themselves. It changes what is possible to know, what is possible to imagine, and what is possible to create. Its evolution is the story of human progress, unfolding discovery by discovery, generation by generation, always reaching toward a deeper truth that lies just beyond the horizon. Quantum physics stands as one of the most transformative intellectual achievements in human history because it challenges the very assumptions that once formed the foundation of classical science. For centuries, the world was explained through predictable laws, solid objects, and straightforward cause and effect relationships. Reality seemed stable, continuous, and governed by principles that anyone could observe with their own eyes. Classical physics offered a comforting clarity. Planets followed defined orbits, objects moved with calculable forces, and light behaved as a wave propagating through space. It was a world that made sense because it could be directly visualized. Yet, as scientists probed deeper into the structure of matter, they found that nature did not follow the intuitive rules that once appeared universal. At extremely small scales, the behavior of particles defied classical expectations, revealing a realm that was probabilistic, discontinuous, and profoundly interconnected. Quantum physics emerged not to replace classical physics entirely, but to expand and deepen the understanding of how the universe works, showing that the classical world, while powerful, represents only a superficial layer of reality. The journey into quantum theory began with mysteries classical physics could not explain. Blackbody radiation, the photoelectric effect, atomic spectra, and the stability of atoms all presented contradictions that classical mechanics struggled to resolve. Light appeared to behave like a wave in some experiments, but like a particle in others. Atoms emitted light in discrete frequencies rather than continuous ranges, implying that energy was somehow quantized. Electrons seemed to exist in stable orbits around nuclei, despite classical predictions that they should lose energy and collapse inward. These anomalies were not minor inconsistencies. They signaled that the classical world, was incomplete. Each new puzzle pushed scientists to question deeply held assumptions, eventually leading to a conceptual revolution. Quantum theory introduced a new understanding. Particles could behave like waves, waves could behave like particles, and the act of observation could influence the outcome of an experiment. This was not merely a new category of physical behavior. It was a fundamental shift in what scientists meant by explanation. In classical physics, objects had definite properties whether or not they were observed. An apple fell because gravity acted continuously upon it, and its trajectory could be calculated with perfect accuracy if the initial conditions were known. In quantum mechanics, the location, momentum, or state of a particle could not always be described with absolute certainty. Instead, these properties were represented by probabilities until they were measured. This idea challenged the very notion of objective reality as a fixed, fully knowable structure. One of the most striking challenges to classical assumptions was the principle of uncertainty. In classical mechanics, position and momentum could, in principle, be known simultaneously with unlimited precision. Nothing prevented a scientist from measuring them as accurately as desired. But quantum mechanics showed that this was impossible. The more precisely one knew a particle's position, the less precisely one could know its momentum, and vice versa. This relationship was not a limitation of measurement tools. It was a fundamental feature of nature. Reality itself was woven with uncertainty, not because scientists lacked skill, but because the quantum world encoded information differently than the classical world. Another profound challenge came from the dual nature of light and particles. Experiments such as the double-slit experiment showed that electrons, photons, and other particles could produce interference patterns typically associated with waves, yet also behave like localized particles when detected. This duality forced scientists to abandon the idea that objects must be either particles or waves. Instead, quantum entities possessed a dual character, behaving as waves during propagation and as particles during measurement. This phenomenon contradicted centuries of classical reasoning, which assumed that objects must have a single, consistent form of behavior. The concept of superposition added another layer of complexity. In the quantum world, particles did not simply occupy one state or another. They could exist in multiple states simultaneously. An electron could be in two places at once, spin in two directions at once, or exist in multiple energy levels at the same time, until a measurement forced it into a specific state. Classical thinking had no room for such a concept because classical objects could not occupy two mutually exclusive conditions at the same moment. Superposition represented a new kind of existence, one that demanded a deeper lens on what it means for something to be at all. Perhaps the most dramatic departure from classical assumptions came from quantum entanglement, a phenomenon where two or more particles become linked so that the state of one instantaneously influences the state of the other, no matter how far apart they are. Classical physics insists that information cannot travel faster than the speed of light, and that objects separated in space should behave independently. Entanglement violated this intuition. It created a form of connection that transcended distance, suggesting that quantum systems do not obey the classical idea of separability. Instead, they exist as unified wholes, with properties that cannot be explained by analyzing individual parts. This contradicted the classical belief that complex systems can always be understood by breaking them down into simpler components. These quantum challenges did not destroy classical physics. Rather, they revealed its limits. Classical physics still works perfectly well for everyday objects, engineering, technology, and astronomical motion. It remains an essential tool for describing the macroscopic world. But quantum physics showed that the classical picture is only an approximation accurate at large scales, but incomplete at small ones. Classical assumptions such as determinism, locality, and continuity turned out to be special cases of a much broader quantum framework. The deeper lens offered by quantum physics revealed that the universe is structured more subtly than once assumed. This new perspective has profound philosophical implications. Classical science envisioned a universe governed by deterministic laws. Given the initial conditions, the future could be predicted with perfect accuracy. Quantum mechanics replaced this certainty with probability. Events no longer unfolded in a strictly predetermined fashion. Instead, they evolved according to likelihoods defined by wave functions. This shift challenged the belief that the universe is fundamentally predictable. While quantum mechanics is not random in the sense of pure chaos, it is governed by precise mathematical rules. It introduces a level of indeterminacy that classical science could not accept. Quantum physics also altered the role of observation. In classical thinking, measurement is passive. It reveals properties that already exist. In quantum mechanics, measurement is active. It shapes the outcome of the experiment. The observer becomes part of the physical process, influencing the state of the system. This idea unsettled many early scientists because it seemed to blur the boundary between objectivity and subjectivity. Yet experimental evidence confirmed again and again that the act of observation plays a defining role in quantum systems. As quantum physics matured, it expanded from a strange theoretical domain into a practical foundation for modern technology. Quantum principles explain the behavior of semiconductors, lasers, magnetic resonance imaging, atomic clocks, and much more. They power modern electronics, communication systems, and scientific instruments. Today, quantum physics is driving new frontiers such as quantum computing, quantum encryption, and quantum sensing. These technologies exploit phenomena like superposition and entanglement to achieve capabilities far beyond classical limits. The practical success of quantum theory reinforces its conceptual depth, demonstrating that the challenges it presents to classical assumptions are not philosophical curiosities, but reflections of fundamental reality. The deeper lens provided by quantum physics also reshapes our understanding of nature's interconnectedness. Classical science described a universe composed of independent objects interacting through forces. Quantum science describes a universe composed of fields, probabilities, and interrelations where objects sometimes lose their individual identity. In this new view, reality is not built from isolated units, but from interactions. Particles emerge from fields, properties arise through measurement, and systems behave as wholes rather than collections of parts. This perspective aligns with the idea that reality might be fundamentally relational, a concept long explored in philosophy but now grounded in physics. Quantum theory does more than challenge classical assumptions. It challenges intuition. It forces scientists, philosophers, and thinkers to reconsider what it means to know something. The quantum world cannot always be visualized through everyday experience, because it does not operate by familiar rules. Instead, it requires abstract mathematics and conceptual flexibility. Yet, despite its strangeness, quantum theory has proven to be the most accurate and predictive scientific framework ever developed. It succeeds precisely because it digs beneath the surface of classical phenomena to reveal the deeper mechanisms behind them. The ongoing challenge is to integrate quantum mechanics with classical theories and with gravity, forming a unified, coherent picture of the universe. Efforts such as quantum field theory, string theory, loop quantum gravity, and quantum information theory aim to connect the microscopic world with the macroscopic one. These explorations continue to push the boundaries of explanation, showing that quantum theory is not the final word, but a gateway to even deeper insights. The importance of quantum physics lies not only in its ability to describe small-scale behavior, but in its capacity to reshape human understanding. It teaches that reality is more complex, more subtle, and more interconnected than classical assumptions allowed. It encourages humility in the face of nature's mysteries and inspires curiosity about the structures that lie beyond our current knowledge. Through quantum physics, science gains a deeper lens, one that reveals the intricate, probabilistic, and dynamic fabric of the universe. As human understanding continues to evolve, the quantum perspective will remain a guiding force, reminding us that the world is not always what it appears to be, and that the deepest truths often emerge where classical intuition reaches its limits. Quantum physics expands the horizon of explanation, showing that reality contains layers of richness that only become visible when we dare to question our most familiar assumptions. In the classical world, measurement is a simple act of looking at something that already exists in a definite form. A stone sits on the ground whether anyone sees it or not. A planet orbits the sun regardless of telescopes watching it. This idea feels so natural that it seems unquestionable. But as scientists explored the quantum world, they discovered that observation does not merely reveal a pre-existing state. Observation participates in creating the outcome itself. This realization overturned centuries of scientific thinking and forced a new understanding of how reality behaves at its deepest level. At the heart of this revolution is the idea that quantum systems exist in a spread of possibilities until they are measured. A particle does not have a single defined position, momentum, or state before observation. Instead, it exists in a superposition of states, mathematically described by a wave function. This wave function represents all the possible outcomes the particle could take, blending them into a unified whole. When a measurement occurs, the wave function collapses into one specific outcome. The remarkable implication is that the outcome does not exist in a definite form prior to the act of measurement, meaning the observer plays an active role in shaping reality. This is not magic, but a deeply rooted feature of quantum mechanics that has been confirmed repeatedly through experiments. One of the clearest demonstrations of this principle is the double-slit experiment. When particles such as electrons or photons pass through two slits without being observed, they produce an interference pattern on the screen behind something waves do, not particles. This indicates that each particle travels through both slits at once, behaving like a wave exploring multiple paths simultaneously. But if detectors are placed at the slits to observe which slit each particle goes through, the interference pattern disappears and the particles behave like classical objects, passing through one slit or the other. Simply observing the path changes the outcome. The particle's behavior is not determined until someone, or some instrument, looks. This baffling result shows that the act of measurement is not a passive process, but an intervention that reshapes the phenomenon. The role of observation becomes even more profound when one considers that it applies not only to particle position, but to all quantum properties. The spin of an electron, for example, can be in a superposition of up and down until measured. Once measured, the electron instantly adopts one of the two possibilities. Before measurement, the electron has no definite spin. After measurement, the spin becomes real and fixed. Thus, the observer does not merely discover the spin, they help define it. This does not mean the observer causes the spin in a conscious way. Rather, the interaction between the measuring device and the quantum system forces the system into a definite state. This understanding challenges the classical belief in objective, observer, independent reality. In the quantum world, measurement is an active event, a physical interaction that directly affects the system being measured. Even sophisticated experiments designed to minimize interference cannot eliminate this effect, because the disturbance comes from the very nature of quantum interactions. Photons, electrons, or atoms cannot be probed without influencing them. The moment energy or information is exchanged between a measurement device and a particle, the delicate superposition of possibilities collapses into a singular outcome. This leads to another foundational insight. Measurement does not merely produce outcomes, it defines what outcomes are even possible. Different experimental setups create different kinds of measurements, and each type of measurement selects a different set of possible results. For example, measuring a particle's position yields one kind of outcome, while measuring its momentum yields another. But the two cannot be known together with unlimited precision because the act of measuring one disturbs the other. This is the principle of uncertainty, which states that certain pairs of properties are fundamentally linked in a way that limits simultaneous knowledge. The observer must choose what to measure, and this choice influences the nature of the particle's state. Thus, the observer shapes not only the outcome, but the very context in which the outcome can exist. The influence of observation extends even further through the phenomenon of entanglement. When two particles become entangled, their properties are linked regardless of distance. Measuring one particle instantly determines the state of the other, even if they are separated by vast distances. This instantaneous linkage suggests that measurement has a non-local impact, affecting distant systems in ways classical physics cannot describe. The second particle's state is not fixed until the first is measured. Once again, observation does not simply uncover information. It actively brings the outcome into existence. The observer's measurement completes the entangled system's state, turning potential correlations into actual ones. This deep involvement of observation has led to different interpretations of quantum mechanics, each trying to explain why measurement has such a powerful role. Some interpretations suggest that reality splits into different branches for every possible outcome. Others propose that wave function collapse is a physical process triggered by the act of measurement. Still, others argue that information is the key ingredient, and that quantum events are fundamentally informational exchanges. Although interpretations vary, they all agree on one point: measurement plays a central and indispensable role in shaping quantum outcomes. The implications of this principle go far beyond the laboratory. They challenge traditional ideas about determinism, suggesting that the universe at its core is not a rigid machine, but a dynamic interplay of possibilities. They raise philosophical questions about the boundary between observer and observed, and whether reality is inherently participatory. They also open technological avenues that would be impossible in a classical world. Quantum computing, for example, harnesses superposition to perform calculations that would take classical computers millions of years. Quantum cryptography uses measurement's active role to detect eavesdropping, ensuring perfectly secure communication. These technologies rely on the fact that observation changes quantum states, turning what might seem like a philosophical curiosity into a practical advantage. In the end, the quantum principle of observation teaches that reality is not simply waiting to be discovered. It is continuously shaped by interactions. At the deepest level, nature is not a static picture, but a process, a dance between possibilities and the moments when possibilities turn into outcomes. Measurement is the bridge that connects these two realms. The observer becomes part of the story, not by imposing will, but by participating in the physical processes that define what reality becomes. Quantum mechanics invites us to see the universe not as a collection of fixed objects, but as a dynamic field of potential, one that reveals its shape only when observed. Probability, uncertainty, and non-determinism reveal that the universe operates through patterns far more subtle than classical predictability suggests. In the quantum world, events do not unfold in a fixed, predetermined sequence. Instead, particles exist within a landscape of possibilities, each outcome shaped by probabilities rather than absolute certainty. This does not mean nature is chaotic. It means nature is richer, layered with hidden structures that only become visible when we accept that uncertainty is built into reality itself. Quantum systems evolve through wave functions that describe all potential outcomes simultaneously, and these probabilities interact, interfere, and shift as particles encounter one another. What may seem random on the surface is in fact governed by deep mathematical order. Non-determinism invites a new perspective, showing that events can arise from multiple pathways rather than a single, fixed cause. This flexible framework allows complex phenomena such as entanglement, tunneling, and superposition to exist, each revealing a universe where possibility is as fundamental as actuality. By embracing probability and uncertainty, science uncovers structures that classical thinking could never reach, offering a more complete picture of how the physical world truly behaves. Modern physics expands scientific explanation by revealing layers of reality that classical thinking could not access. As scientists probe deeper into the universe, they discover that familiar concepts like space, time, matter, and energy behave differently under extreme conditions near the speed of light, at the smallest quantum scales, or in powerful gravitational fields. These discoveries show that the world is not built on simple, universal rules, but on structures that shift depending on scale and context. Relativity reshapes our understanding of motion and gravity, demonstrating that time stretches, space curves, and energy transforms in ways invisible to everyday experience. Quantum mechanics exposes a world of superposition, entanglement, and uncertainty, revealing behaviors that challenge intuition yet accurately describe atomic and subatomic systems. Together, these frameworks broaden what counts as a valid scientific explanation, replacing rigid, deterministic models with flexible, multi-layered ones. Modern physics shows that no single viewpoint captures the entire truth. Instead, different theories illuminate different aspects of reality, each essential for understanding the universe's complexity. This expansion does not discard classical ideas, but incorporates them into a richer, deeper picture of how nature operates across all levels.